I'm really excited to be with you all virtually. So I am going to talk today about the detection of large-scale cloud microphysical changes that we've observed within a major shipping corridor due to the implementation of the 2020 International Maritime Organization's new marine fuel sulfur regulations. So it's kind of a mouthful. So we're going to go through each part of that to see where we're at. But in terms of where this is going, it's actually exactly in that introduction in terms of how can we use these kinds of natural experiments in the Earth system to learn about our climate and about cloud physics in particular. Okay, so what were these marine fuel regulations? So it turns out that ships burn basically the dirtiest stuff that no one else wants to burn, which makes sense, right? Very few people live out in the middle of the open ocean. So if we do have something kind of at the bottom of the barrel there, that's probably where we would want to burn it. And so in terms of stuff we really don't want, sulfur is pretty high up there, right? We don't want to be breathing in sulfur. So marine fuels traditionally have been really high in sulfur content compared to other fuels. And that's been changing. So in the blue curve here, these are limits that were imposed within these emission control areas. These are like just small regions off the United States and European coasts for air quality reasons. But the kind of bulk of shipping out on the open seas, you were allowed to burn things up to 4.5% sulfur by mass up until 2012. Since then, it's been about 3.5% by mass. And now in 2020, there's a 1-year 7-fold drop from that 3.5% limit to a 0.5% sulfur mass limit. And we expect this to have some pretty big effects, some really good. So there are anticipated to now have been air quality benefits, especially for coastal regions. So if you look at the US here, besides kind of around where I'm at in Florida, relatively small changes, again, because we already had that emissions control areas around our coasts. But especially if you start looking at Eastern Asia, South Asia, these areas over here, we're expecting a lot of avoided excess mortality because of these air pollutions that really negatively affect these coastal communities. So that's awesome and is a pretty straightforward, good news story of environmental regulation. Unfortunately, everything comes with a catch. So to achieve these air quality benefits, there is believed to be a warming trade-off. And sometimes the media has spun this a little bit of an unexpected trade-off, but I just want to point out that this was anticipated. So this paper here is actually from 2009, thinking about these, what we were going to do from a long time ago. And the issue here, so ships burn fuel, warming effect from CO2, global shipping, something like 3% of CO2 emissions. But much larger than that, at least in the short term, is their cooling from that sulfur, actually, which here you can just see in a very simple emissions climate model, is a much larger effect, at least in the first couple of years. So by reducing the impacts on health, we're potentially shifting the climate effect of ships from previously a cooling, at least in the short to medium term, to a net warming. And why is that? And it has to do with how ships affect clouds. So essentially kind of the conundrum is this IMO 2020 regulation, despite having these amazing air quality benefits, could potentially be accelerating global warming by reducing ships' effects on clouds. And kind of the poster child, not just for the ship's effects on clouds, but kind of for aerosol effects on clouds in general, or where aerosols are any kind of liquid or solid particulate in the atmosphere, are these ship tracks, shown in the sidebar that you might have noticed over here, as this is a modern satellite image from just several years ago, versus here, this is the very first image in the scientific literature of these ship tracks, all the way back from the mid-1960s. This paper is super cool. It was written by an Air Force guy, so they were hypothesizing that these quote unquote anomalous cloud lines could be secret missile trails or ship smoke screens. And the reality is much more, I don't think boring, but probably a normal person would think boring just in terms of these pollution particles getting into the clouds. And these ship tracks have been really useful for testing hypotheses about what we'll learn about the Toomey effect and adjustments to the Toomey effect. But their overall climate significance was really uncertain until recently. So let's take a step back and try to think about, why do we care about these ship effects on clouds? And these marine low clouds in particular, we'll see, are the real big players in what I care about from cloud physics. So clouds, at least in terms of Earth's energy balance, have two main effects. In the first plot here, you could see the different blues here are the cooling effect of clouds by reflecting sunlight. So sunlight that otherwise would be absorbed by the surface is instead being reflected back to space by clouds. Clouds also warm via the greenhouse effect. So clouds emit at a cooler temperature than the surface and therefore trap infrared radiation in the Earth system, preventing that from leaving to space, leading to a net warming. And what you can see is that both of these have pretty large values. When you put them together for the net cloud radiative effect here, the cooling wins out, and it wins out in these very particular areas. And the global average cooling effect of clouds is about -20 watts per meter squared. A useful benchmark to have in the back of your head is that the instantaneous forcing from doubling CO2, if you just went out and magically doubled CO2 in the atmosphere right now, is something like 4 watts per meter squared. So the net cooling effect of clouds is 5 times larger than a doubling of CO2. And obviously no one's talking about completely getting rid of clouds or anything like that, but this is just kind of to show that anything that perturbs the net cloud radiative effect could have a fairly substantial lever on climate, just given how large it is. And when we're thinking about what makes up that net cloud radiative effect, the vast majority actually comes from these low-lying clouds. So they're low-lying and therefore have a relatively weak greenhouse effect, but they're still very optically thick and therefore reflect a lot of sunlight. And you can see kind of the hot spots here, some in the southern hemisphere, like this stratocumulus deck here off the coast of Western Africa, but also here off the coast of California, the North Pacific, and the North Atlantic. And we'll see when we start talking about shipping again and seeing where these shipping corridors are, that's going to become really important. So how do these aerosol cloud interactions work? So that's kind of clouds in the base state. Why do we care about how aerosols perturb them? And that's because aerosols can make these clouds reflect more or less sunlight than they were going to before. And here, I'm very specifically talking about aerosol cloud interactions in these low altitude, generally warm phase clouds. We're gonna ignore ice microphysics for right now. So imagine you're out over the remote ocean. There's not much around, right, in terms of little particles in the atmosphere, maybe some sea salt that's being kicked up by the wind. Turns out every cloud droplet needs some kind of seed or cloud condensation nucleus to form around. So let's say you're given the task to build a cloud and you have some amount of liquid water you get to work with. Let's just hold that constant for right now. The only thing you can really do is create a cloud with a relatively small number, relatively small number of relatively large droplets shown schematically here. This is a pretty inefficient way of spreading out your surface area for that given volume of water. So that cloud's not really that bright, or as bright as it could be. Now let's say a ship comes through and is spewing out thousands upon thousands of little particles from its smokestack, from burning fuel with a lot of sulfur in it, and then having that sulfur deposit on those particles and produce these really great cloud seeds. Now, for the same amount of liquid water you're playing with, you can create a cloud with a much larger number of smaller droplets. And that's a much more efficient way of spreading out that surface area, which makes a more reflective cloud. And you can get enhanced cloud cooling because of that. As you could imagine, that the statement, imagine you have some amount of liquid water to play with, is doing a lot of work here. And part of the reason we or that I'm still employed in looking at aerosol cloud interactions in warm clouds, is that's not the only thing that can happen. We also have adjustments to the Toomey effect, where if you had a cloud that was naturally drizzling, it turns out that these large particles are relatively good at coalescing together and producing precipitation-sized droplets that start falling out with gravity. If you have a bunch of little droplets instead, they're much less efficient at coalescing with each other and actually producing these precipitation-sized particles. So you could imagine if your ship goes through an area that was naturally drizzling before, maybe now you're shutting off that drizzle and that cloud is either keeping more liquid water within the cloud, or maybe that cloud sticks around for longer because it's not raining out and losing its liquid. We could also have the opposite effect happen, though. So in a cloud that's not heavily drizzling in the base state, it turns out for a couple of different reasons, these smaller particles, especially when they're near cloud top, are easier to evaporate. And that enhances the entrainment or the turbulent mixing of dry, warm air from above the cloud down into the relatively moist and cool cloudy layer, evaporating the cloud. So the drizzle suppression effect would tend to enhance the cooling from the Toomey effect, whereas the entrainment effect would tend to counteract the cooling. And we don't really know which one of those effects wins globally. And that's part of the reason we have these really big error bars on our aerosol cloud interaction. So this is kind of the famous plot from similar versions in the last couple of IPCC reports, where we have the carbon dioxide and the well-mixed greenhouse gases here, warm colors for warming. We have our aerosol cloud and smaller aerosol radiation interactions down here, cool colors for cooling. And if we look at this kind of total error bar on the total anthropogenic or human-made forcing of climate in the present day, the main contributor to the width of this error bar is from aerosol cloud interactions in particular. So why are these aerosol cloud interactions so uncertain, especially because we already have these amazing ship tracks, right, that are teaching us everything we need to know? So it turns out it's more complicated than that, even just with this case of ship tracks, where we have this a little bit surprising result where ship tracks, at least until recently, estimates have been they really don't make much of a difference at all globally. So this image here is from a paper from 2007 looking at manual detection of ship tracks for a year of satellite data. And what they find is when you very painstakingly map out each of these lines, right, and find out its albedo perturbation and add that all up, you get a global forcing of a fraction of a milliwatt per meter squared. Again, for doubling of CO2, that's 4 watts per meter squared. So a fraction of milliwatt, something we basically don't care about. So that's a little weird, but okay, maybe these ship emissions are an interesting curiosity, helpful for hypotheses, but maybe they don't tell us much more. But maybe it's also the case that these well-defined ship tracks are just kind of the tip of the iceberg, and actually what we need to be looking at is kind of the integrated effect. And we can maybe look over shipping corridors. That's what this paper tried to do about 10 years ago from Peters and colleagues. They looked at 3 shipping corridors over here. The colors here are showing you where a ship is based on their sulfur emissions. And what they did is they chose these corridors specifically because the meteorology here sets the winds perpendicular to these corridors in general. So what they did is they looked at this boundary layer wind as it's moving towards the shipping corridor, so a presumed clean environment, and after the corridor, so a presumed polluted environment. What you'd want to see there is basically a big jump in these cloud properties due to this pollution, where if we remember that Toomey effect cartoon, what we would expect is a greater concentration of droplets after hitting that shipping corridor, or a smaller size. And you don't really find anything. It's just noise. And they did this with a couple of years of satellite data. They wound up going back and doing this in a climate model that they knew had a bigger effect, and found out that just because of the natural variability in the system, this method was not able to actually detect a signal, even if it is there. So that's kind of a bummer. And it's even weirder because we do get a really sizable forcing when we put these ship emissions in climate models. And here I'm just going to show one model because it actually spans the whole range of the literature estimates just from using 3 different plausible emissions of shipping sulfur, which are showing at the top. And from these, you get something between negative 0.2 watts per meter squared, negative 0.6 watts per meter squared. So some substantial fraction, up to 40%, at least in this paper, of the total forcing from aerosol cloud interactions coming from shipping and being really localized in these areas of high shipping and low cloud coverage. So what gives? And it turns out we've found out over the last few years. So there have been recent advances in observing ship effects on clouds. So I'll talk a little bit about those and a little bit about what they've told us so far about the effect of these IMO 2020 regulations and where my work fits in. So the first new advance is looking at enhanced detection using machine learning techniques. So instead of having people painstakingly manually find all of these lines, we're going to have a machine learning algorithm do it instead. And when you do that, there are two different algorithms that have been published. You can see here relatively similar results between the two of them, even though they were developed independently. And both of these databases find over an order of magnitude greater density of ship tracks than that previous paper did that was looking at manual identification. So we can use this to learn about the IMO 2020 effect on shipping, hopefully. And it turns out, as we would expect from the basic physics, is that there was a big reduction in the frequency of these detectable ship tracks after IMO 2020 went into place. And the reason for that is even though you still have these small combustion particles that the ships are burning with this now cleaner fuel, you don't have the sulfur that's helping those particles grow to sizes where they become good cloud seeds, and also the chemical properties of that sulfur coating the kind of organic gunk that gets released from the direct burning also helps make those particles good cloud seeds. So we have a pretty big reduction in the frequency of ship tracks. And if we look at cloud droplet number concentration, which is the top here, what we find is a big decrease in 2020 compared to years before. So that's great. That's exactly what we would expect. And here, it's probably easier to see here in this non-ECA is the open ocean, so that these not emission control areas. Big decrease in cloud droplet number concentration, which corresponded with a decrease in effective radius, which is not supposed to happen. If you remember the cartoon, these are supposed to be anti-correlated. What we'd actually expect is larger sizes now in these ship-affected clouds with this reduction in the ability for these particles to seed the clouds. And we find no change in cloud brightness, which is very confusing. So we would expect that clouds with less number concentration would be darker than they were before. So that's a little weird. Let's move on to that Watson-Paris paper. They also find a big reduction in shipping here, zeroing in on the Southeast Atlantic here. If you look at the actual number of ship track occurrence, it goes from a couple hundred down to about 75 here. But if you just look at kind of time series of the cloud droplet number concentration observed from satellite over these areas, you really don't see anything that's that different from the pre-existing trend. Maybe if you squint in the Southeast Atlantic, but it's not very convincing. Okay, so what else do we have? There's a new method that I'm not going to unfortunately have time to talk about in that much detail today, locating quote-unquote invisible ship tracks by actually tracking air masses that have been identified as affected by ships. And that paper is really interesting because you can actually see in these quote-unquote invisible or undetectable, is maybe a better word, ship tracks, you have very different responses in both cloud droplet concentration, a little bit weaker, but also in terms of the total amount of liquid in the clouds. So that's super interesting and something we'll get back to at the very end here. But what we'll talk about for the rest of this seminar is a third method developed recently from my group and collaborators, creating quote-unquote counterfactual cloud fields over a shipping corridor. And you might be thinking to yourself, Michael, we just talked about this and it didn't work. Didn't you just tell us that? And there are reasons why it works in specifically the Southeast Atlantic, where it did not work in the Petters et al. Papers. And to give away the punchline right now, it's because the winds here, instead of blowing perpendicular to the track, are blowing parallel to the track where all of these ships are going by. So we have this big kind of ship superhighway right here. You can see in the yellow. winds that are constraining the pollution to be relatively close to where it was emitted on the track, or at least in line with where it was emitted on the track, and relatively clean areas on either side. And because of that, I'm showing here the results that we got in our previous paper demonstrating this method. We can look at the contrast between the factual or kind of actual observed or in reanalysis in the first plot here situation from satellite reanalysis. We have surface sulfate mass over here. You can see the shipping corridor pretty clearly. Cloud droplet number concentration with, at least in this area here, we have most of these low clouds. You can see what looks like a pretty suspicious line of increased cloud droplet number concentration and decreased effective radius. What we're going to do is we're going to take the surrounding areas that we believe are not affected by ships, at least in the shipping corridor, and use their spatial statistics to create this counterfactual situation where what would this area look like if that shipping didn't exist? And I'm going to go through the details here, but just kind of to show you how this works in the result, we can interpret the difference between the actual situation and the counterfactual as the causal effect of ships in the shipping corridor. And we see an extremely statistically significant increase in surface sulfate, increase in cloud droplet number concentration, and decrease in radius, exactly what we should expect from the Toomey effect. But for the first time in this paper from 2020, we're able to see a significant, meaningful effect on a regional and spatial scale and climatological temporal scale, which was really exciting. So what we're going to do next is apply that to the post-2020 period, because when this paper was written, we did not have this data, but we did actually predict that we might see a change. So let's see what happens. And before we get to that, just a little bit about how this method actually works. Now that I show you, we should, if we do believe that it works, it produces some exciting results. So let's kick the tires a little bit and see if it actually works. So the statistical method I'm using is called universal creaking, where this is a classic, and it was actually first, or the basics of it were developed in the early 1900s. Geostatistical method to estimate some variable at an unknown spatial location using nearby observations of the same variable. So the way we actually implement this is we have a mean function or some quote unquote mean value. Here we're taking it from a regression model, and we're training that regression model with different geographic factors, so latitude, longitude, and a couple permutations between the two, so where you are spatially, and some cloud controlling factors. And by cloud controlling factors, I mean meteorological factors that influence cloud properties that we already understand fairly well. In the case of the new post-2020 work, what we're going to look at are 3 cloud controlling factors: sea surface temperature, shown as the pre-2020 climatology up top, and then just differences from the climatology, which, as you can see, are small compared to the mean values in the bottom. The white dots here means that's significant compared to the pre-2020 standard deviation. Estimated inversion strength, which is an estimate of how strong that capping inversion, keeping the warm, dry air above the clouds from mixing in to the cool, moist cloud layer is, and the wind speed, so how quickly these winds are moving. I used slightly different but similar variables in the 2020 paper, so not a huge difference. But that mean function, again, is from latitude, longitude, and these cloud controlling factors. So in addition to that, we are also going to assume that the error or noise around these mean values is spatially correlated as a function of the distance between locations. And we're going to formalize that with a semi-variogram, which don't worry too much about fully internalizing this right here. But basically what we're showing is this is the formalization of stuff looks more similar when it's close, or stuff close together looks more similar than stuff further away, is basically what this equation is telling you. And we're fitting this with an exponential. So these black values here are the binned observations of how these values look next to each other. And we have a parameter for kind of how quickly the spatial dependence decays with distance. And we have this SIL parameter here for basically where does that level off? And that fits our spatial function. 2 other things I'll just note. The 2 variables we'll be talking about here are the cloud effective radius, which I introduced previously, how big these cloud droplets are, or the effective measure of how big they are. We're also going to look at cloud albedo, here specified by a cloud, so how bright the sky is, specifically when clouds are present. And technically, this is the cloudy sky albedo. So I'm just looking through the whole atmosphere from space. How bright is the sky when these clouds are present? And we're going to do some statistical transformations that we're going to make the variogram work a little bit better, but we're going to retransform it in everything I show you. But I kind of wanted to air all the dirty laundry here. The last thing that I just want to mention, it's a little bit different from the previous 2020 paper, is we're going to broaden the area that we consider to be ship affected. And part of that is because of just in general, this is a new paper out looking at tracking ships by their kind of satellite tracker, which is a very expensive data set to gain access to. So very nice to have some of these figures here for cargo ships in particular. And there are good questions about what happened during COVID. Were there big changes in shipping? And it turns out it's actually a little bit of a wash. There are some increases and some decreases. They're actually not large compared to the base amount, but specifically in the shipping corridor here, it looked like there was a little bit of an interesting spatial shift to the west of where these ships were. So we're going to shift our shipping affected box a little bit to the west compared to where we were previously, just to make sure we're catching that and not seeing any weird edge effects. Okay, so with that, here are our results. And for right now, these maps are only showing results for the one season that happens to have the highest signal, austral spring. So because it's the Southern Hemisphere, September, October, November. I have a couple theories for why that's the peak season, but this is the easiest way to illustrate it. Later on, I'll also show some values for the annual mean as well, with the thought that we're dealing with a signal to noise problem, right? So let's look at the season with the highest signal, and let's look at the annual average that should theoretically have the lowest noise. So in the top here, we have the pre-2020 climatology. And in the first column, we have the actual observed values for that climatology. We have the counterfactual, so what I explained before, where we're taking these values on either side of the shipping corridor and interpolating in between using that spatial statistics Kriging method. And the difference, which we're interpreting as the causal impact of the clouds here. And here, this p-value I'm calculating based on are the number of statistically significant grid points here, marked by these white dots, larger than what we would expect by chance. So if you just have a couple, you might get that by chance. If you have almost the full 70 points that are available, be significant, that's pretty clearly something weird is going on in that shipping corridor as opposed to the areas around it. If we look at just 3 years before the IMO regulations, let's see basically how noisy is this. Can we actually get a signal out of it? And it turns out it is a little bit noisier, but you get what is a pretty convincing corridor signal and still very highly statistically significant. So now let's see what happens if we add in the 3 years after 2020. So 2020, 2021, and 2022, where if implemented as we expect, ships should have much less sulfur than before. And that's what we see down here, where we have the observations, this counterfactual, and the difference. And the first thing that should hopefully jump out at you is the effect of shipping on shrinking the size of these cloud droplets has dramatically reduced entirely, at least within our ability to detect it in this northern area, and quite substantially in the southern area. Although we are still picking up some effect, but much reduced compared to where we were before. So that's an exciting result, right? Because as we mentioned before, these ship track results showed something qualitatively similar, but couldn't quite get us to the cloud properties themselves. So this is pretty strong evidence, at least in my argument, that we're already seeing a large-scale cloud microphysical effect, at least, from these regulations. And we're also seeing an effect on the brightening of the ships themselves. So what we can also see is it's a little bit noisier, but in the climatology, in the blue here, we have a substantial brightening effect of the clouds, so clouds with higher albedo due to the effect of these ships than they would have otherwise. A noisier, but still pretty convincing signal in the 3 years prior, and a noisier and a little bit more random, if you kind of look at the spatial area here, effect. But just by eyeballing it, this is a little bit less of a slam dunk, right, than the cloud effective radius. So what we're going to do is we're going to define a core shipping corridor area, so the 3 grid boxes in the center of this affected area, and average over that. And we're going to compare not just the immediate 3 years and the 2020 to 2022 3 years, but all available 3-year periods, just to see how much of this post-2020 effect could be just due to chance because of this smaller sampling time frame. So when we do that, we get this. And here again, I'm showing results for the austral spring. On the top here, I'm showing relative change in RE, effective radius, so the size of the cloud droplet, so this shrink that we have in the climatology and this gray shading, and the change in cloud brightening, so this increase in cloud brightness that we have in the climatology. And the different years will appear here as different colors in a second. And the level of statistical significance, what you'll see is that basically everything is statistically significant. It's statistically significant by standard metrics, but just to label the strength of them, the most statistically significant will be solid, kind of moderate in dashed, and the weakest ones will be dotted. So these colors here are just showing the kind of spread we can get by chance in all of these from the dark red 2002 to 2004, 3-year period, in the blue, this most recent 2017 to 2019 period. You can potentially try to convince yourself there may be some trends in here. I'll just tell you now, when you look at the annual, it kind of reverses. This is basically noise to the best as I can understand it. And so essentially, this is between this 2002 and 2008 curve, right? It's kind of how much spread we're just getting naturally. And everything's overlapping with the climatology, at least quite a bit. And same in the cloud albedo. When we add in the 2020 to 2022, in cloud effective radius, kind of 2 things pop out. One is, by far, it is the weakest effect on record. It actually does not overlap any of the other curves within its 95% confidence intervals, and very clearly does not overlap the climatology within its 95% confidence interval, unlike the previous years. It's also the only one of these curves that is not statistically significant at the highest level. So again, all different pieces of evidence that this effect is substantially weaker post-2020 than in any prior 3-year period of the recent past. And again, as we saw before, less of a slam dunk, but still a pretty convincing signal in cloud brightness. Again, the weakest year on record, and the weakest year by a bit more than what you just expect from this kind of natural variability in the prior years. And again, a little bit weaker, although some other prior years were just as weak in terms of their statistical significance. So that's austral spring, where again, we have kind of the highest signal. Look at annual mean, where we have theoretically the lowest noise. We get something very qualitatively similar, although again, because the signal is a little bit weaker, a little bit more overlap, but a pretty, again, the weakest decrease in effective radius on record, and the weakest increase in cloud brightness on record, although for the annual mean cloud brightening effect, not necessarily as much of a showstopper as the other ones. One other point I wanted to make about the cloud brightening here, the 2020 to 2022 curve is actually the only one that's not distinguishable from 0 at 95% confidence. So in terms of thinking about detectability, in the paper, I decided to make life hard for myself and go by a two-tailed test of 95% confidence. So here I'm just kind of showing that it's a table in the paper, which looks less pretty. Here I'm showing that schematically as these PDFs of, in the red here, the austral spring effective radius, in the orange, the austral spring cloud albedo, purple or blue and purple, the same for the annual mean. And this is just the ratio of the 2020-2022 shipping perturbation over the effect in the climatology. So we have something like a 1/2 to 1/3 decrease in the magnitude of this effect in austral spring for the effective radius, highly significant, very obviously significant at 95% confidence. For cloud albedo, just missing the mark in terms of significance at 95% confidence in a two-tailed test. It would actually meet the bounds for a confident detection of a decrease in the effect size if you went with a one-tailed test. Just in retrospect, probably what I should have done for good statistical reasons. And And again, the annual mean ones for effective radius, you actually still are statistically significant either way. But again, this annual mean one is not quite statistically significant. We probably need more years of data to be able to say something stronger at the annual mean. So one implication of this is it can help us monitor compliance with IMO 2020 limits. So the plot I'm showing here is kind of the data we have right now, where the IMO essentially just pays consultants to go out and test all the fuels of the world. And when they did that and reported back, the points here are what they got for the average fuel sulfur content by mass on the market. So about 2.5% previously. So actually not at the legal limit even. But since 2020, they've been just a little bit over or around 1% by mass. So a big change. And if you look at the fraction of fuel oil that's compliant with the sulfur limits on the market, only 20% of the fuels that were on the market would have been compliant with these limits before, and now it's somewhere between 70 and 80%. And these compliance values are actually underestimates because there's also an alternate way of complying with these regulations is rather than burn cleaner fuel, you can also capture the sulfur with a scrubber. So theoretically, the only ships that should be sailing and burning these non-compliant fuels are ones with scrubbers that hopefully they are scrubbing and then maybe more unfortunately releasing that wastewater. So again, everything is trade-offs. But again, this is kind of, trusting that this monitoring is working. In this paper, I'm arguing is, in addition to the ship track studies, one form of geophysical monitoring, which can be quite powerful. So here on the y-axis, I'm showing the austral spring mean effective radius averaged over the whole Southeast Atlantic region, where the black is this observed value and the blue diamonds are this counterfactual with the 95% confidence intervals here. And again, our smallest change in 2020, where again, these cloud droplets in this counterfactual or without shipping should be a little bit larger. Let's imagine a hypothetical world in which the IMO 2020 regulation was not enforced. And the way we're going to do that is take this counterfactual estimate that we calculated and apply the average or the climatological 2002 to 2019 difference. So the shrinking effect of effective radius due to the ship emissions pre-2020. And that gets us this red X. This is where we would expect to be in the real world if IMO 2020 was not put into effect. So this delta here, this increase in effective radius compared to what we would expect without the shipping emission is what I'm arguing, the true effect of these IMO regulations. So about over this whole region, a 0.1 micron, or about close to, well, 1% increase. If we had instead did something like what, not to pick on them, but the Watson-Paris paper did, and just kind of use a persistence forecast of, okay, what was this doing before? We're just going to estimate that it would have been doing that. So we would expect it would actually be somewhere down here, or maybe just take a persistence forecast of the 2017 value. This is what we would expect it to be if there was no change. And if we actually observed this non-compliance value, which again is higher due to changes in background meteorology or something else that's not the IMO 2020 effect, we would incorrectly estimate that the IMO 2020 was having an effect of 0.3 micron increase in cloud effective radius when the true value is 0. So just kind of to show that you actually do need some of these fancy statistics, or you could be pretty substantially misled just by trying to look at time series by themselves. Even though this effect is it's pretty sizable, but it's on the order of natural variability. So that's why we need these more sophisticated statistical methods. The other thing we might care about is how much forcing did this actually create? And here in the shaded curves, you don't have to worry too much about what's actually happening in this equation, but the important thing for the shaded curves is this is a function of the effective radius estimates we have. In the lines, this is a function of the cloud albedo estimates we have, which again are a little bit more uncertain, but they are kind of telling the same thing, right? Wherein the climatology here in blue, we had a more substantial cloud brightening effect that agrees fairly well between the effective radius estimates and the cloud albedo estimates. That has decreased in the 2020 to 2022 period. And if we look at that decrease as the causal effect of the IMO 2020 regulations, what we find is a regional perturbation on the order of 1 watt per meter squared. So quite a bit higher than that in the season of kind of maximum signal in the austral spring here, and something more like half a watt of meter squared regionally within that shipping corridor, if you just look at the annual mean. And this agrees relatively well with global climate model estimates of global forcing. And it agrees with the climate models much, much better than those previous manually detected ship track studies. So orders of magnitude more forcing, now directly observed, but also in kind of buttressing these global model estimates. And these global model estimates, again, if you remember from the previous slide, were on the order of 0.1 watt per meter squared global effective shipping. So if we take that about 50% reduction, again, we're thinking of an order 0.1 watt per meter squared global forcing, but regionally much higher. How does that affect current rates of global warming? There's been a lot of interest in the media and on the web app formerly known as Twitter in terms of what the IMO 2020 regulations are. What do they possibly mean for current climate? There's probably a blip, but our best estimates are it's small, especially compared to current warming, but also things like the El Nino La Nina cycle and also the solar cycle. Similar in magnitude, actually, to the stratosphere water vapor from Hunga Tonga, interestingly enough. So something we care about, but not something that should be obvious in just a time series of global temperature, at least. But again, maybe quite more important for regional warming, where here, these are the North Atlantic temperatures anomalies in July and this giant spike in 2023. It's quite plausible that the ship emissions, because they're so concentrated in here, the North Atlantic and the North Pacific, might be some decent fraction of this spike, even though the forcing here is kind of just getting going. And the final implication I'll talk about here is for solar climate intervention. So there are these proposals that have now been looked at by the US government, and there might even be formal research programs put into place by the US government in the next few years to look at, can we offset some of the effects of increasing greenhouse gases in the atmosphere by reflecting sunlight back to space? The answer is very clearly no for can we offset all of the effects, but can we offset some of the effects? And the way people have proposed doing that are putting sulfur up in the stratosphere or recreating this shipping effect in marine clouds, but with a different natural aerosol like sea salt. So when I was at NOAA, I asked, what would we actually need to look at for this? And this IMO effect, I think, is going to really help us think about local cloud adjustments, signal detection for some of these changes that we might expect, and also where are these clouds susceptible? If we can see them in this IMO effect, then these might be the areas that would be targets for a hypothetical marine cloud brightening proposal. And I realize I'm already, I think, at where we should be for getting to questions. So I'm going to just very quickly give you 2 very quick tastes of the next steps here. These macrophysical adjustments. This was a big part of the 2020 paper, something that I've not yet tackled with the post-2020 data, but it turns out in the satellite, I was only looking at the Terra satellite, which overpasses in the morning. And there, we did not see any changes in the total amount of liquid making up these clouds. But in the afternoon, we did, and we actually saw that these clouds were being made up of less liquid water in the afternoon than we would have expected without shipping. And that offsets a lot of this effect. So if that is really happening, and if that happens with other aerosol effects, then the total forcing from aerosol might be lower than we would have expected otherwise. And we have a current proposal looking at, can we combine this method, looking at the shipping corridor as a whole and kind of this bottom-up method with the machine learning ship track detection, and see if we can get some better resolution on these adjustment questions in addition to the Toomey effect results I showed today. So with that, I'm going to leave the key takeaways up while opening it for questions. Thank you so much for listening.
Thank you so much, Michael. At this time, if anybody has a question, if you want to go ahead and type it in. I see a couple raised hands. Tim, I'll let you take it away. Or sorry, that's Jay. Let me make, yeah. Perfect. Tim, do you want to go?
Yeah, sure. That's a wonderful talk, Michael. Thank you very much. Very clearly presented. I think my chief concern that perhaps, I mean, maybe I'm out to lunch, but hopefully you could address it, is that in both in the Kriging and for the counterfactual and in the regional calculations, it looks like you're assuming that the ship tracks are an effect that is dynamically independent of its surroundings, in the sense that the ship tracks do not enact some sort of, let's say, radiative perturbation that has an impact on the dynamics and hence the thickness of the clouds that are outside of the ship tracks. The ship tracks and the surroundings are effectively considered as two totally independent quantities, which I don't think they can be. And indeed, if you look at some ship tracks, you sometimes see dark bands, for example, around brighter ship tracks and their surroundings. And I'm sort of trying to muddle through this, but it seems to me that that would exaggerate the effect that you're talking about working through it, though I may have thought about it wrong. But anyway, I mean, do you have any comments on this? Is this potentially an aspect of the problem that should be given more careful consideration?
Yeah, thank you for that question. I think it's a really good question. It's something that I think is a limitation of this kind of work. So basically what Tim's getting at here is, okay, we kind of see this decreasing effect, or we have all the ship tracks in the corridor here, but if we are indeed getting some substantial brightening effect here, do we have dynamical adjustments outside? So we have a cooling effect here, and is that going to affect clouds on either side in the larger scale? And I think that that's really hard to address. One way that we are trying to get it, at least at the smaller scale, is, at least for most of the plots I showed, focusing on the internal part of the track and kind of ignoring these flanks, where I think some of these effects might be going on, and that maybe require kind of their own more detailed look. The very small scale effects, and actually you can maybe even see it a little bit on the sidebar here, so where you have these this open cellular convection and this kind of like speckly white here, and then the ship track, which looks very solid, and then this kind of band of blue. Hopefully the projector is high enough resolution that you can see this well. That might be a local cloud clearing right next to the ship track. The spatial resolution here is 1 degree by 1 degree. The resolution, or the thickness of these ship tracks, is about 20 kilometers. So I think within the core shipping corridor area, I should be catching those. I hope, at least. That does keep me up at night a little bit in terms of these machine learning methods. So if you look here, this is the red here are the tracks with Tianli Yuan's method, and the blue are kind of the control pixels right around the track. And those control pixels very well might be picking up some of those, at least local scale dynamical adjustments. And we're actually, in the project we're starting now, going to look at that explicitly, because I think that is a concern, and try to look at local adjustments as you move further away from the track. For those regional scale adjustments, that's a lot harder, and I don't necessarily have a great idea for addressing it. Maybe we can talk about it tomorrow. But that's also, I think, one of these big questions for marine cloud brightening in general, is, are you going to get risks of circulation effects that your cooling in one place is just going to cause warming in another, and basically kind of cancel themselves out and be unproductive or counterproductive? I think that's an unanswered question.
Thank you.
All right. Jay, do you want to ask your question, and then we'll do Alex after that?
Yeah, sure. Can you hear me now? Yeah, sorry.
There we go, sorry.
No, excellent. Excellent. Very, very intriguing talk. I wonder, I mean, it seems to me that you can't consider the Toomey effect in the absence of the Albrecht effect, which is precipitation. Because once you change the cloud microphysics from smaller effective radii to larger with the fuel, you're likely going to start a more active drizzle process. And I wonder if that's been part of your thinking, because just in a very simple from a very simple perspective, you would expect the cloud fraction to go down, or the liquid water path to go down, and maybe that's what you're finding in those last thing you were saying. But certainly, I think the precipitation should be responding to the change in effective radius.
Yeah, and something that's been on my to-do list for a while is actually look at or use this Kriging algorithm directly on satellite measured precipitation, particularly Ryan Eastman's drizzle product, which I think would be really cool to see if we get a nice signal from that. So part of the reason I focused on the Toomey effect for this paper was basically, again, kind of hot off the presses, right? This is using data just from December 2022, so very, very new. And kind of from the 2020 paper, we had this result that at least in the morning, we did not seem to have any statistically significant changes in liquid water path or cloud fraction, at least in that paper using the earlier methods in the morning. So I was thinking that at least to get a first cut at the problem, to try to limit some of these questions we have around adjustments, we could use the Terra data as our hopefully close approximation of a pure Toomey effect. What's actually happening here might be a little bit more complicated. So there is good or some really interesting like diurnal cycle work in large eddy simulations in some similar regions, looking at a diurnally varying adjustment term where you actually have an increase in cloud liquid water path overnight when drizzle maximizes in aerosol perturbed clouds that transitions to what we see here in the actual decrease in liquid water path during the day because of that increased entrainment effect that's more active when you actually have more solar burn off, essentially. And at least in that paper, these effects basically cancel them out at our small magnitude in the morning. And I think we might be seeing observational evidence of that, and kind of that morning no adjustment effect might actually be the cancellation of those two diurnal effects. That's something that I would like to address explicitly, and I think we have the data that we can address it explicitly. But yeah, it's on the to-do list.
Very good.
Great. Alex, you want to ask your question? You're still there, Alexander? He said he's here, but I can't hear him. If you're talking, we can't hear you. All right. Is there any other questions? If you want to type it in, Alex, you can go for it. I'll give you a second.
You have the Q&A open as well as
yeah, I've got it open right in front of me so I can see it. All right. He wanted to say he's good friends with Lily and to say hi to her for you. All right, if there are no other questions, we'll go ahead and thank our speaker with a virtual round of applause. Just me. Here we go. So thanks so much for coming, and thanks so much for that talk, Michael.
Yeah, thank you so much for having me. And for those of you I'm meeting with tomorrow, I really look forward to it.